Hello, dear friends. Welcome to this important and beautiful discussion where we are talking about chemical equilibria. So, we have to understand that chemical equilibrium is a state in a chemical reaction where the rates of the forward and reverse reactions are equal, resulting in no net change. There is no any net change in the concentrations of reactants and products over time. Therefore, at equilibrium, the system is dynamic. It is dynamic in a way that reactions continue to occur, but the amounts of reactants and products remain constant. So now we have to understand that this is a very important area in advanced level chemistry. So the applications where we find chemical equilibrium very important is in the Haber process. The Haber process is a process through which we do synthesis of ammonia. So synthesis of ammonia is also very important since ammonia itself forms a foundation on which most of the explosives and fertilizers are made. The other process that is very important is the contact process. And the contact process is a process through which we do manufacture of sulfuric acid. The other important process where we have the application of this chemical equilibrium is what we call the Oswald process. That is a process through which nitric acid is manufactured. There are many processes, including even methanol synthesis. Methanol itself is a solvent and can be used as a fuel, and so the process through which we manufacture this methanol requires us to understand the processes through which the chemical reactions are occurring so that we are able to design processes or put measures in place to ensure that we have an optimized chemical reaction. So in our discussion, the key concepts that we are going to be looking at is that we need to understand dynamic equilibrium. These reactions are not going to be static, not static. They are going to be in a dynamic equilibrium because reactions will continue to occur. Yes, the reactions will continue to occur, but the concentrations of the reactants and products do not change. Then the second concept that we need to understand is the equilibrium constant. This is going to be the quantitative measure of the position of equilibrium. We will be knowing whether by using this equilibrium constant, we are able to know that now the products we have more of the reactants or we have more of the products. That's what the equilibrium constant can help us to tell. Then Le Chatelier's principle is also another principle that is very important, and it states that if a system is at equilibrium and is subjected to a change in concentration, temperature, or pressure, the system will return to adjust itself to counteract the change and restore equilibrium. So that is Le Chatelier's principle, and this is a very important concept that we will have to also understand, though the details will be discussed in the future. So now to begin our discussion fully, we are going to consider reactants, or we are going to consider this reaction where we have A that is forming B, and this is going to be a reversible reaction. In other words, the products at B side, at state B, can recombine to form A. That's what this represents. While in the rest of the chemical reactions, we use a full forward arrow. In chemical equilibrium, we don't use a full forward arrow, but we use these arrows, one pointing this side, another one pointing forward, because we are going to be having both forward and reverse reactions taking place. That is, if we have conditions that favor the recombination of products back to reactants, or we are presenting conditions that favor the formation of products from reactants, that is in the forward reaction or in the forward direction. So here we are saying A can convert to B or B can convert to A. Now at equilibrium, because this is what we are interested in, at equilibrium, we'll find that the rate of forward reaction is equal to rate of reverse reaction. So this is a very key concept that we must understand, that at equilibrium, the rate of forward reaction is equal to the rate of reverse reaction. Now, here, the concentrations of both A and B are constant. In other words, they are not changing. Now, a chemical equilibrium, as we have already said, is a form of dynamic equilibrium and is not static, meaning much as we are having these concentrations not changing, okay, the reactions are taking place or the reactions are occurring either forward or backward, depending on what we want. If we want forward, then we shall provide conditions that favor the forward reaction. And therefore, we will find that usually, once equilibrium has been attained, if the rate of reverse reaction is known, then we can tell the rate of forward reactions because the two are going to be equal at equilibrium. Now consider two cities, for example, P and Q. We could be having two cities. We have city P, and this city P has got maybe 2,000 cars. Then we have city Q. Okay, this city Q maybe has about 1,000 or let me say 4,000 cars. If we have cars flowing from city P to city Q, and maybe these are 10 cars per hour, and then we have 10 cars per hour. When you look at this scenario, this city P represents the concentration of maybe reactant A or reactant P, and in city Q, we are representing the concentration of of the product Q. So if we are having equilibrium, you'll find that the concentration of P and the concentration of Q are going to be the same because the rate of forward reaction is the same as the rate of backward or reverse reaction. Because here you are having 10 cars entering city Q per hour, meaning that even after 10 hours, the number of cars in here are going to be the same since you are having 10 cars per hour leaving city Q. Likewise, at city P, you have 2,000 cars. So you have 10 cars per hour leaving and 10 cars per hour entering, meaning they will remain the same. So that is very simple demonstration of what happens at equilibrium. That is, it is analogous to reactions at equilibrium. So to demonstrate this further, let us draw graphs to represent the concentrations of A and the concentration of B. So in all cases, at the very beginning, the concentration of, we are talking about reactants, for example, P and Q. So at the first, if I have this reaction, at first, we have zero concentration of Q, but we have P in abundance. And therefore, the reaction has no choice other than going in the forward reaction path. So we are going to be having, first of all, Q increasing and P reducing. So this is going to be our P. And if you have visited reactions on rates of reaction, you'll find that we have products and reactants. The products are going to be increasing and reactants are going to be reducing. And you'll find that all of them, you have either an exponential decay for reactants and an exponential growth for products. So likewise for Q, we are going to have something like this. So usually you have an increase, this is Q, an increase, and then you reach a steady state. Then you also have a reduction in the reactants, then you also reach a steady state. So here, this represents equilibrium, and then here, Q will stop rising, and also P will stop falling. That's what we have to understand here in this graph. Now let's continue and see what happens at equilibrium. Let's draw our graph to represent what is existing at equilibrium. So this will go to equilibrium, and also this is going to reduce up to equilibrium. So this is P again, this is Q, and these are concentrations, this is time. So at this point, the rate of forward reaction is equal to the rate of reverse reaction, and this is equilibrium. So equilibrium has been attained, and so we are having the concentrations of P and the concentration of Q not changing, and then we are finding that the reaction is proceeding with time. So you'll find that for this case, the concentration of P falling, whereas the concentration of Q is rising. Here, you'll have rate of forward reaction equivalent to equilibrium constant K1 times the concentration of P, and then here you have also the rate of reverse reaction that we are calling equal to K inverse K, then times Q. But we know that the rate at equilibrium, rate of forward reaction is equal to rate of reverse reaction, meaning I'm going to have K1 into P is going to be K inverse into Q. So I divide both sides by this K minus 1, and finally I will have K1 divided by K inverse equivalent to the concentration of Q divided by the concentration of P. So here we have concentration of products divided by concentration of reactants, and we will find that this is represented by capital K E2, which represents the equilibrium constant. This is where we get the equilibrium constant, and is always going to equal to the concentration of products divided by concentration of reactants from now and onward. So if we have a reaction as follows, you have A plus B giving you C plus D. Let's insert the stoichiometric factors. So this has A, this has B, this has small c, and this D. What happens to the rate of reaction at equilibrium? You'll find that at equilibrium, we say the rate of forward reaction is equal to rate of reverse reaction, and therefore the equilibrium constant K will be represented by we have Kc, which is in terms of concentration. So in terms of concentrations, the equilibrium concentration constant is going to be, now we said it is always going to be concentration of products divided by concentration of reactants. So this is going to be C times concentration of D divided by concentration of A, which are the reactants, times concentration of B, and then we are going to raise these ones by their stoichiometric factors. So I have C here, D, I have A, I have B. That is one. If we have gases reacting, in other words, instead of us having general reactants like you have solutions, you have solids, here we are going to have gases. Now, if we have gases, we no longer Okay, we can express gases in terms of concentration and partial pressures. But what is always very important that is easier to deal with are the partial pressures of each gas. Therefore, we will have the equilibrium constant in terms of partial pressures. So meaning that Kp is going to be, we are going to be taking the partial pressure of reactants divided by partial pressures of products divided by partial pressures of reactants. So this is going to be, obviously we need to raise them by the respective stoichiometric factors. So this is going to be Pc to power C times Pd power small d divided by Pa power small a, then times Pb power small b. And that gives us the equilibrium constant in terms of partial pressures. So these two equations are going to be very, very paramount in our proceeding examples, where we are going to be involving examples on how to apply these constants.